Here we are. As I said, we're going to go across the periodic table. The term for this is what you see on the slide, descriptive chemistry. The study of the elements and the compounds that they form. And as the section title is, elements by the groups. So we're going to look at the groups. Now, before we get into that, because sometimes I may say the wrong group, all right? When I learned it, we had what's called the North American Convention. This was the 1A and the 2A, and then the P subgroup over here was 3, 4, 5, 6, 7, and 8A, because that was how many valence electrons. And then the transitions were called the B groups. And this didn't have any group names. The F's just went back in there. But the IUPAC is, as you see here, 1 through 18. So, I mean, my 3A is now group 13, and 4A, 5A. So it's basically, if you take 10 away from this number, you know how many valence electrons. 1 valence electrons, 2, these are not, they're inner, they're transition, 3, 4, 5, 6, 7, 8. So that is the difference in the group names from the past recording of this course and now, because it has become less in favor to use that North American and more to use the IUPAC. And so that's what they've gone to in labeling the groups. So as we go across the groups, we'll use those numbers 1 through 18. We're going to start out with the hydrogen group, a group by itself. Why? Why is lonely old hydrogen? Notice how it's even a little bit separated, and that it's that way in your periodic table too. Did you notice the little bit of space there? Yeah, and it's a different color. So is hydrogen the same as the rest of those in group 1? No. Now I want you to think why that is. And hopefully you can come up with the answer. I'll give you a couple clues as we go through. So here's some basic information on hydrogen. It's the lightest and most abundant element. It is a gas at room temperature. It only has one total valence electron in its one level shell. And it can easily gain another electron, or it can lose the electron it has. So it can be, now notice they have 1 negative or 1 plus. You would, again, I learned many moons ago, little Indian lingo there, -1 and +1, and now it's 1 negative, 1 positive. So if I ever write it that way, same old, just no difference in that. So those are some things about hydrogen. Now what is its physical, what are its physical properties? Colorless, odorless, tasteless gas. Tasteless. You think about it. Have you ever had something that had, a slightly disagreeable odor, but you were in its presence constantly? What happens after a while? You don't smell it. So I can't be absolutely sure that hydrogen does not have a smell, because it may just be our nose is not sensitive to it. But when we say odorless, that's what we mean. We don't respond to it. If you, and there's like of the air that is hydrogen. So if you were breathing a 10% hydrogen container of air, it wouldn't have a smell to it. My little thing on odorless, and the same thing with tasteless. Is it something that our taste buds just don't respond to? But maybe other animals, animals do have. No. Next, diatomic. Now there are 7 diatomic gases, and as we go through this, we'll talk about them. You'll hear them popping up from time to time. This is the first of them. Next, it has a very light mass. You know, hydrogen is a very light element. And it says it can move. It has to move at high speeds. And because it is so light and also small, it will diffuse. It will go through very quickly because of its size and because it's moving faster. Why does it have to move faster? Because it's at the same temperature. That means temperature is the average kinetic energy. So if here's a heavy gas, here's a light gas, they're at the same temperature, they're the same average kinetic energy. What's kinetic energy? 1/2 mv squared. If the m is very small, the v has to be very big. Yeah. So the lighter the gas, the higher the speed. There you go. Now, hydrogen, we don't breathe that. Do we breathe helium? Yeah, helium's a light gas. And what happens when you breathe helium?
When you talk like this, you can wonder, why do I have this funny voice?
Because it is so light, the molecules are moving so fast that your vocal cords are bouncing around faster with a lighter, faster moving gas, and you have a higher pitched sound. So that's the lightness of and the speed concept there, using the concept of kinetic energy, the formula of it. Okay, next it's chemical properties. It reacts like the group 1 and the group 17 elements. That's a hint as to why it's by itself. And I gave you another one earlier that I didn't tell you which one it was. Next, it can combine with various other elements to form important compounds. A halide, that means an element plus hydrogen, a halide. Hydrocarbon is hydrogen and carbon. And we will study hydrocarbons in the organic chapter. Next, it can become unstable at high temperatures and pressures. But if you have a very low temperature and a super high pressure, you can make something that's very exotic called metallic hydrogen. And we're looking into using that as a propellant. It's just so dangerous. But it's also very, very potent. It has a very high specific impulse, a lot of thrust per weight from it. But that's just neither here nor there, other than that we're working on it. Now, have you figured out why hydrogen is by itself? What is different about hydrogen that is here in the group 1 than lithium, sodium, potassium, rubidium, cesium? All of them have 1, 1, 1, 1, 1, 1, 1 for the last number in their electron configuration. So they all have that 1 valence electron. So what's different about it? What's different in the first energy level, the first shell, than all the other energy levels? Okay, think about sublevels. The first energy level has S. Does it have a 1p? No. Does the second energy level have an S? Yeah. Does it have a 2p? Yes. 3p, 4p, 5? That's the difference. So what do you get in the first level? You have 1 proton, 1 electron, hydrogen. 2 protons, 2 electrons, and we're not dealing with neutrons. 2 protons, 2 electrons, helium. You're done. So hydrogen is literally halfway full and half empty at the same time. It has 1 of 2. So it can lose that 1, as your note said, that was the other hint. It can lose the 1, it can gain the 1. If it loses the 1, it's just the proton from the nucleus. If it gains 1, it becomes like helium. So there's nothing in between. When you look at the periodic table and you look at the top, what do we have? Is there anything up here? No. So there's hydrogen, there's helium. So that's what's different about hydrogen, because it has only the S sublevel in the first energy level. Then it can lose 1 and be like the other ones that are underneath in the group 1, but it can also gain 1 like a group 17, like fluorine, grabby. Now, is hydrogen as grabby as that? No. We could look up the electronegativity value of it. We won't take the time to do that. You can check it and see, but it's nowhere near as high as fluorine, even though it's smaller than fluorine. So if you think of hydrogen as being able to be in both places, both above the lithium and above the fluorine, like a group 1, a group 17, it doesn't exactly fit into either of those categories because it's 1 out of 2. All the other ones are 1 out of 8 or 7 out of 8. 1/8, 7/8, 1/2. Yeah, it's kind of in the middle, even though it's all the way over here. So hydrogen is by itself. Next, we're looking at group 1A, the alkali metals. There they are. Notice that's everything underneath hydrogen. Alkali metals. What are their physical properties? Shiny, soft solids, low density, so they're not really heavy. They're very good conductors of heat and electricity. Now, is that what you think of when I ask you for a metal? Light and soft. No. How soft are these? They're like if you take not margarine, but butter out of the refrigerator. You can cut it with a knife, but it's got a lot of resistance to it. So, is that the way metals are? So these are not the typical, the common metals that you think of, but these are a chemist's metal. Why? Because of their chemical properties. They're very chemically reactive. They only have 1 electron out of 8, as I just mentioned, which is easily lost. So they're going to form 1+, positive 1 cations. They are so reactive you will never find them pure. This is a very how should I say, evident inverse relationship. The more active an element is, the less likely it is for you to dig in the ground and find it pure because it's already combined with something to make a compound. Is gold very active? No. Can you dig in the earth and find gold? Yes. Not very commonly, but you can find it. Okay. Can you find a chunk of sodium? Nope. It will have reacted. It will not be elemental anymore. It will be in a compound form. And it is very difficult to store because it is so reactive. Can you have a lithium with a 2+? No. It only has 1 outer electron. And if it loses that outer electron, it says 2-1. What happens if it loses that? Then it only has 2 electrons, which makes it like the group 18. These, the alkali, they are the boom, spit, fizzle, spit, boom, dud. So fizzles really everything over to here. And then we've got a spit, a boom, and a dud. These are duds because that level is full. Well, what happens when lithium with 1s2, 2s1, what happens when it loses that 2s1? It becomes like helium, which is 1s2, a full level. So that is the technical term, you don't need to know this, isoelectronic. So the alkalis are very reactive because they just have that 1 electron. Please, please, lose the electron. Please, take it from me. Okay? That's why they're so reactive.
Welcome to Periodical Estates, the home of the atom families. In Townhome 1, you'll find the elements with 1 valence electron. At the top is hydrogen. He doesn't quite fit in with the others, the alkali metals. Not only is he a gas, but he's also highly flammable. No birthday parties for him. Lithium lives 1 floor below. He spends his time making high-performance batteries. Sodium and potassium are both very active. They're often used as electrolytes in sports drinks. On the bottom 3 floors are rubidium, cesium, and francium. Cesium is great at keeping time. In fact, he works hard to keep atomic clocks accurate. The alkali metals are all very generous. They won't hesitate to give up their valence electron to another element in need. For the most part, Group 1 is a big, happy family. That is, as long as none of the alkalis turn on the water.
Next, the group 2, the alkaline earth. There you see the 2. Notice that's again those half dozen that starts in the second energy level. So it's 2s2 and 3s2 and all that. What are their physical properties? Denser than group 1, harder than the group 1, but they're still malleable. You can still, kind of move them around and that. Higher melting points. Everything that is extreme in the group 1 is going to be less. So the group 1 is the lightest. This is heavier. The group 1 is the softest. This is a little harder. The group 1 is the most active. That's chemical. This is less active. And that's the chemical properties. Reactive, but less than the group 1. Why? Because you have 2 valence electrons. It says they are easily lost, but is it as easy to lose 2 as it is to lose 1? No. So yes, they are easily lost, but not most easily lost. That's the alkali. Boom! Group 2, spit. Okay? Boom, spit. They're going to react, but not with a boom, because you do have to lose 2 electrons. And when you lose the first one positive, it's harder to lose the second one. Here's the slide on that. They form the cations, as do the alkali, with a +2 charge. Let's go ahead and let's meet the alkaline earth metals.
Welcome back to Periodical Estates. In Town Home 2, you'll find the alkali metals' cousins, the alkaline earth family. These elements have 2 valence electrons. Beryllium likes to help other metals make ultra-strong alloys. She's also immune to X-rays. They pass right through her. Magnesium likes to show off during the holidays. He is responsible for a lot of fireworks. Calcium is much more laid back. He helps to make bones strong and healthy. He's also really into chalk. Strontium and barium like to get together with magnesium and put on a show. Strontium takes care of the red fireworks and barium the green ones. Radium doesn't need a nightlight. She glows in the dark. She used to make glow-in-the-dark watches, but now she's found a career in medicine, helping to treat bone cancer. The alkaline earth metals aren't quite as active and reactive as their cousins, the alkali metals, but they still have trouble holding on to their valence electrons.
Next is the transition metals, the group 3 through 12. All of those, what do you got? 40 that are in there. 4 sets of D sublevels. That's what they mean by transition. Okay, let's look at the periodic table. We've got 3s2, 3p6. 4s2, now we go back into the 3d. So it's a transition as we fill up the 3, and then you jump back out to the 4th level and fill up the 4th. So transition, going back and filling in the D level from the D sublevel from the level underneath. That's what it means by transition. Their physical properties, they are solids at room temperature, except for mercury, that's a liquid. They're dense, they're hard and strong, they're shiny, they're good conductors of heat and electricity, they are ductile and malleable. Now, these are your common metals, your typical metals: iron, copper, cobalt, nickel, zinc. Most of them are found right here. Do you think of sodium as a metal? No. That's a chemist metal. because it loses electrons. These are the common people's metal, okay, that are what you think of as a metal as you were growing up. So those are in the transition area. The chemical properties, they're varying in their reactivity. You know, some of, like iron will rust if you put pure iron in water, it will rust in hours. It will react. Will gold rust? Nope. So from nothing to very, very slow. So boom, group 1. Spit, group 2. Fizzle for all of the transition and even the post-transition metals that we'll see later. All right, and they have 1 or 2 valence electrons. There might be an exception, but we're not going to deal with it. They form cations, either +1 or +2. They are usually pure in nature because they are pretty low in their reactivity. Fizzle. All right, it's time for us to finish up by meeting the transition elements in their periodical estates.
A large family lives in the D block of periodical estates. In townhomes 3 through 12, you'll find the transition metals. They're quite a diverse bunch. One of the things they have in common, though, is that they're constantly losing their electrons. When they can keep a hold of them, most of the atoms have 2 or 3 valence electrons. The transition metals are usually dense, shiny, and great conductors of electricity. Some, like gold, silver, and platinum, have admirers throughout the world. They're practically celebrities. Others are known for their strength and dependability, like iron, copper, and tungsten. Many of the others have unique properties that make them stars in the electronics industry. The transition metals have a lot to offer, but keep your distance from the ones on the bottom floor. They're all radioactive.